Good morning, students. Myself is Adarsh, and today we are going to start with organic chemistry. But before starting, I would like to congratulate you to come to the very much right place. Reason being that we all are having a well-defined, organized structure for the preparation of every aspect. Now, coming on to the organic chemistry section, when we want to talk about organic, I guess the major difficulty that we all are facing, reason being that some of the fundamentals, some of the basics are somewhere either converted to misconception or they are somewhere lacking. When it comes to the major difficulty that most of us are facing, I guess if I would like to ask you, you may definitely reply that in the comment section that what is a major difficulty that you all are facing. One, very rightly pointed out, in the acidic strength of the compound. Two, the basic strength of the compound. In some of the section, the difficulty that we face is about crowding some of the structural parameters which are being affected by the crowding, and there are few more aspects in terms of when it comes to organic chemistry. Somewhere we got confused about nucleophile and base, which one is strong, when it is strong, and certain things about some of stereoisomeric portion. Because if we go beyond this section, then I would say organic chemistry is mostly about reactions and relative products which are getting formed in the reaction. Essentially, I believe some of you might be facing difficulties in some of the products where we have to choose on which product is major, which product is minor. But all those things which are related to reactions are somehow based on the foundation and the fundamental of the organic chemistry. And when it comes to very fundamental thing, then I would like to explore one thing today in very much detail, and that thing is today basic concept behind acidic and basic strength. Because see, when I talk about one acid, I'm saying it is given a compound, whether it is an acid or it is not. How do we choose? If any one of you can reply in the comment section clearly. I can definitely go and read that. So when it comes to acidic strength, we used to say any substance that gives H+. But in that case, some information takes over. For instance, the information that takes over is Lewis acids are also there, sir. Bronsted acid are also there. Arrhenius acid are also there. So to rectify that information, I will tell you, first of all, our most common solvent is water. So we predominantly stick to Arrhenius information. Second, then we are discussing about relative acidity. Then somebody is losing proton, somebody is accepting proton. So that information predominantly depends on proton donation and proton acceptance. So ultimately, when it comes to discussion of organic chemistry, predominantly we are concerned about two definitions here. One is Arrhenius, another is Bronsted. And I know that, let us give a highlight on that. Basic concept of acidic and basic strength. In organic compounds. Although we are talking about organic compounds, but that is not very much consistent with the organic compound that is applicable to any type of compound that we are going to share, any type of compound that we are going to discuss. When it comes to, as I said, In organic, what do we consider? We consider two types. For organic acid is H plus donor, and I am not mentioning the solvent here because we know whether it is Arrhenius or it is Bronsted. The two main concepts that we said will be covered in the organic section are referring to those acids or those bases which are we are going to deal in organic chemistry only. So likewise the bases mostly H plus acceptor. Whatever be the case that we will discuss about acid and base, in that case we will see H plus donor is acid, H plus acceptor is base. That is what primarily we will try to stick to when we are dealing with the organic chemistry. Now coming on to general aspect, because we know this very well. When it comes to acidic and basic strength, that is very well driven by the equilibrium. For acid, if I would like to write one equilibrium that you all might be very much familiar of writing H plus A minus. So in this equilibrium, you know this, there are few parameters that we can define very clearly. One is called Ka. That is the equilibrium constant for the dissociation of this acid. Another we defined as pKa, which is nothing but minus log base 10 of Ka. So the sign indicates if Ka is bigger, pKa is smaller, and if this equilibrium constant is bigger, the acid is going to be stronger. Very simple, we will say acidic strength is proportional to Ka and is inversely proportional to pKa. Because I know many of us make mistake in some of the question where the question has been given, arrange these four acids in the increasing order of pKa value. If it has been asked in increasing order of pKa value, that simply means I have to arrange decreasing order of acidic strength. Or sometimes the question may be reversed in the increasing order of Ka value. Then I have to arrange them in the increasing order of acidic strength. So first of all, I must be very much careful about this Ka and pKa relationship because that is going to be very important. Now when we come to the second parameter, what is it that decides whether this acid is strong or not? Two things. One, because we have to break this bond. Bond strength of Ha bond. Weaker the bond, stronger the acid. So first of all, we will write acidic strength is inversely proportional to bond strength. That is one thing. Now, if bond is weaker, acid is stronger, that is very clearly evident to us. For example, if I ask you guys a simple question, very basic, that HF, HCl, HBr and HI, and it has been asked, arrange the following in the increasing order or decreasing order of their respective acidic strengths. So what is it that we can figure out here? That Hi bond is weaker because it is the longest bond, then HBr, then HCl and then HF. So, sorry, this order is primarily on the basis of the bond strength, but there is one more parameter. Let us Go back and look at that thing once again. In this case, there is something that is A minus that we have here. And I know that more stable is this A minus, stability of A minus. More will be the tendency of this equilibrium to move forward. Greater is the stability of this anion, more is the tendency of this equilibrium to stay in the forward direction, which simply means stronger is the acid. So the other parameter that is coming out here is acidic strength. Is proportional to stability of A minus, right? When it comes to stability of A minus, again we have many more things to figure out, right? Let us review the whole stuff that we discussed so far. For instance, parameters that we decide to discuss the acidic strength. One, that is about Ka value. Two, that is about pK value. Three, that is about the bond strength. Four, that is about the stability of anion. Now when I am coming on to these four parameters, you all know this very well. These two parameters are numerical based parameter, and I will not have any analytical comparison. I must be provided with some numerical value, and then only I can compare Ka or pKa or the respective things. I hope there is no confusion in this particular section, because that is the section of chemical equilibrium, and we are not going into very much hyped of chemical equilibrium. We are going into very much basic of it, right? So again I am repeating that Ka and pKa is only important for two perspectives. One, that you should be careful in the question whether the information you have to reveal is in the form of Ka or it is in the form of pKa. That is. Second thing, when some of the data is given and there is kind of matrix match, that okay, match the values. One side acids are given, on the other side Ka or pK values are given, and you have to just find a match there. That's it. These two things are important for that perspective. Now coming on to this, the bond strength. When we are discussing primarily our organic acid section, in organic acids you hardly have 2-3 things where you have to take off proton. One, you will take off proton from oxygen. Another, you will in certain cases take off proton from nitrogen. And in certain cases you have to take off proton from carbon. You know that tautomeric examples that we have, lot many. So primarily that bond strength parameter is also not going to be a very major thing for us. Now we are coming on to the final parameter that is going to play a very crucial and a very important role for us. And what is that? The parameter that left here is the acidic strength is proportional to stability of A minus that is formed after loss of proton. Can I say that this parameter is applicable to all the cases? That is very important, because then we have to discuss about the parameters which are actually providing stability to A minus, right? So let's try and focus on that section. When it comes to stability of an ion, then we should primarily be focused that what is it that provides stability to a particular charge. So let us first highlight this section, the kind of acids that we discuss about, that is HF, HCl, HBr and HI. After loss of proton, anion that we are getting is F minus, Cl minus, Br minus and I minus. Now we have to see first, okay, I can compare the strength on the basis of the bond. Since the bond of Hi is weaker, therefore this is going to break easily and it will lose H plus easily. That is one parameter. So this is one part. Other part is coming about the stability of anion. See, when it comes to stability of any anion, we should primarily think on 2-3 things. One, size of anion. For any type of charge, if we have to compare charge stability, we will say lesser is the charge density, more is the stability of charge. Why so? You can think about it. See, a charge reacts only with the oppositely charged particles. If I got a negative charge, it will react only with a positive charge, right? So after loss of H plus, the anion that I got here, what is it intended to combine with? The H plus again. So if the density of negative charge is less, its ability to combine with H plus will be poor. It won't be able to pull back and attract that H plus and recombine with it. Simply what I can say, that stability of anion and size of anion are having a direct relation. Now coming on to the second part, after size of anion, the second parameter that we are here to compare is charge on anion. See, if I have got two anions, one is having 2 unit of negative charge and another is having 1 unit of negative charge, then the anion that has 2 units of negative charge will be able to pull back H plus strongly. The anion that is having 1 unit of negative charge is not able to pull back H plus easily, right? Therefore, I will say if negative charge is less in terms of units, then anion is more stable. So simply I will say charge of anion is inversely proportional to stability. I hope if I want to correlate this with one example that we deal with kind of inorganic acids, then you know, if I have to compare the acidic strength of H3PO4 with H3PO2, then I know that H3PO4 is able to lose 3H plus, H3PO2 is giving only 2H plus, but H3PO2 is a stronger acid. Because the one that lose first H plus easily, the one that form more stable anion after loss of first H plus is more acidic. That means when we have a polyprotic acid, the acidic strength is driven by the first H plus. So this thing we can sum up here, especially when it comes to this particular section. For polyprotic acid, acidic strength is decided by the first H plus. Is governed by first H plus, or you can also tell something about that, Ka1, or you can say pKa1 value. Whenever it has been asked, whenever we have to compare the pK value or the K value for polyprotic acid to decide their acidic strength, it is the first value that is important to us. I think that point must be quite clear to all of you, because these are very basic things, as I said, that we have to make our foundation really strong so that we will not get any misconception ahead. So just briefing all these things for the sake of better understanding. Now, if I have to compare these acids for that sake itself, if we have to compare these acids, I minus, that must be having quite a big size. Then coming on to Br minus, it must be having a comparatively smaller size. Then coming on to Cl minus, that is having a further smaller size. And then coming on to F minus, that is having the smallest among them. So even in the other cases, except for organic acid, if I want to compare acidic strength in terms of this charge density and the stability of corresponding anion, I can very easily correlate all the factors. And that is what I would say is the beauty is that organic chemistry is not separate from chemistry. Only the organic section we are discussing that is included. Rest, it is nothing but the same. Anyway, coming on to the next part here, if we have to compare, for example, stability of an ion, ultimately stability of anion and acidic strength are very much proportionate. And we did relate stability is inversely proportional to charge density. That is one parameter that we so far discussed, stability and charge density. Charge density, we are very clear that okay, larger the size of atom, right, stronger will be the acid, size of atom that bearing negative charge. But problem is, as I earlier mentioned, carbon, nitrogen, oxygen, these are three main atoms that we have to consider primarily in organic chemistry to take out hydrogen from. That means we are taking off one hydrogen, sometimes from carbon, sometimes from nitrogen, sometimes from oxygen. So very simple, when size of atoms are comparable, that is very important for us to discuss here. If size of atom are similar, then what is the next parameter that we have to compare? And that next parameter coming out to be the electronegativity. More electronegative atom is able to accommodate negative charge more comfortably. So we will say stability of an ion is proportional to electronegativity of atom bearing negative charge. So now we are coming on to the, gradually reaching up to the point what we need in organic chemistry. If anion is more stable, acid is stronger. How do we decide anion is more stable? First parameter, we have to compare according to the parameter. First parameter is about the charge density, or I would say the size of atom bearing negative charge. If those all sizes are comparable, not significantly different, that means they are from the same period. carbon, nitrogen, oxygen, fluorine, they are in the same period all along. So I will compare that in that scenario on the basis of electronegativity. And even if electronegativity will be same, then we will see other parameters. But these parameters we are discussing here in the preference order. When I have to say the preference order, the first preference is size of atom bearing negative charge. That simply means if you are getting your answer only on the basis of this size, then you are not supposed to bother by any other parameter. You just answer it and do not give a second thought. Right? The second thing, electronegativity of atom bearing negative charge. That simply means more electronegative atom, if sizes are comparable, bearing a negative charge is more acidic. For example, we are discussing a very clear-cut case here. If we take up H2O, we will take NH3 and we will take C2H2, acetylene. Moreover, we are taking one more thing, and C2H6, that is ethylene, right? So we have mixed up the number of cases. We have taken some of the cases of organic, some of the cases of inorganic, and you know that question comes like that only. So we have to emphasize on that. After loss of proton, that will give OH minus, the negative charge is on oxygen. After loss of proton, this will give NH2 minus, that means the negative charge is on nitrogen. After loss of proton, the negative charge is on carbon. And here also the negative charge is on carbon. But the difference is, this oxygen is sp3 hybrid. This nitrogen is sp3 hybrid. This carbon is sp3 hybrid, sp hybrid. This carbon is sp3 hybrid. So rest of the things are very clear, because usually when it comes to oxygen and carbon, then oxygen will be more electronegative almost all the times. But when it comes to carbon and nitrogen, actually sp3 hybrid nitrogen is less electronegative than sp hybrid carbon. But if carbon is also sp3 hybrid, then we know that very well nitrogen is going to be more electronegative. So out of this particular section, if we have to arrange the acidic strength, I know that the most electronegative oxygen is here. So the most acidic compound is H2O. After that, next most electronegative atom is this sp hybrid carbon, as we mentioned right away. So this is going to be C2H2. But now the comparison left is between sp3 carbon and sp3 nitrogen. And in that scenario, nitrogen is essentially be more electronegative. So this is NH3 and then C2H6. Excuse me. Sorry. So this is how you can decide the acidic strength, and I discussed only two parameters, just size and electronegativity. When it comes to the same atom, that is actually the problem area. Same atom mean if it is always oxygen atom or if it is always carbon atom. if it is always nitrogen atom. And comparison is between different nitrogen atoms, different carbon atoms, and I do not have any significance of electronegativity in those given cases also. Then how do we compare that? Let's look at that part. If the electronegativity is also comparable, if no visible difference in the electronegativity, then it comes to the effects of organic chemistry that we deal. What are those effects? You know that one is aromatization. If after loss of H plus particular ion is going to get aromatic, that is really important. Then it comes to another parameter that we call back bonding, or p pi d pi or p pi back bonding. That also plays a very important and significant role there. Then it comes to resonance also. Then it comes to reverse hyperconjugation or minus H effect also. So there are many different type of effects that we can consider here, and we can go for the comparison, like how to relate these acidic strengths. Let us go for that. See, if we take up this example, I'm just taking one random case. Okay, we have to take up this hydrogen and to compare the acidic strength. We took off this hydrogen. We know that this is anion that we will get, and this anion is getting resonance all around, right? So this anion is in the resonance. I can say yes, this hydrogen must be quite acidic in comparison to, if I look at this hydrogen. Although this hydrogen is bonded to sp2 carbon, this hydrogen is bonded to sp3 carbon, but after loss of this H plus or this H plus, there will not be any difference in the hybridization. Why so? Because this will participate in the resonance, and as an outcome of this resonance, as this resonance happens, all the carbon atom will be sp2. Since all carbon atoms are sp2, now I have no electronegativity parameter, but I have one parameter. When I take off this hydrogen, this one, and form this anion, it doesn't bring any resonance to negative charge after taking off this. But if I take off this hydrogen, not only this resonance, but you all are very well familiar of this example that we call cyclopentadiene anion. So this compound is going to turn to be aromatic. So aromatic, turning something to aromatic is a very significant and a very relevant case when we have to compare acidic strength in multiple cases. If something is going to be aromatic, that simply means removal of that hydrogen is highly favorable, because after removal of hydrogen, the entity which is going to get formed is highly stable. Anyway, so one of the parameter that we discuss is attaining aromaticity after loss of H plus. attaining aromaticity after loss of H plus. That is going to be one of a very, very important and very, very significant parameter for us. Now coming on to the second parameter, which I said and mentioned is very important. That is again a very, very, very good thing. That is participation of negative charge in back bonding. We will come on to that part also if we have to explain what exactly the back bonding is. It is a coordinate pi bond. Simple. A coordinate bond, that means one atom is donor. But since both the atoms which are forming this bond are already bonded by a sigma, therefore this coordinate is going to be pi. One acceptor, one donor, and a coordinate bond formation. So for your understanding, I'll just write it here in one line. It is a coordinate pi bond. And essentially, we will explore later that the property of coordinate pi bond mean what does it mean when a coordinate bond is formed, and what are the conditions required for a coordinate bond formation, what are the conditions required for the formation of a pi bond. That also we will discuss. That is very important because we cannot consider back bonding anywhere. That is also one of very important confusion that majority of kids are having. Sir, somewhere coordinate bond is formed, somewhere it is not formed, somewhere back bonding happens, somewhere back bonding doesn't happen. We will explore that part. Don't worry. We will discuss, get into the details of it when we'll discuss chemical bonding here. But right now I would like to give you one example. See, there is a very famous question. This is CHF3, that is fluoroform. This is CHCl3, that is chloroform. This is CHBr3, that is bromoform. And this is CHI3, that is iodoform. Now in all these cases, I know I have no difference because everywhere the hydrogen is bonded to carbon only. I have to take off hydrogen from carbon, and after taking off hydrogen, the resultant negative charge is going to be on, what do you say, carbon atom only? Right. So in this species, after loss of proton, I will get this, that is CF3 minus. In this case, I'll get this, that is CCl3 minus. In this case, I will get this, that is CBr3 minus. And in this case also we get Ci3 minus. Every case negative charge is on the carbon, and only difference is the atoms which are bonded to carbon. Somewhere it is 3 fluorine, other case it is 3 chlorine, other case it is 3 bromine, and the other case it is 3 iodine. So now we have to look after which one is more stable, and I would like to see if you guys are able to comment in the section that which one should be the most acidic among them and which one should be the least acidic among them. That would really be appreciable if you guys can revert on it, because I would like to understand what is your lookout of these things. How can you really figure out these strength of acids? Although I'm not expecting any right answer, and I'm not disclosing anyone's answer here, that what answer which guy or girls has given. No, I won't disclose that. But I would like to see your comments here. Look at this. The carbon atom bonded to 3 fluorine. All 3 fluorine are pulling electron of carbon towards itself. all the 3 fluorine are pulling electron towards itself, right? Here carbon atom is bonded to 3 chlorine, and all the chlorine are making the carbon electron deficient, the carbon that has got a negative charge. Likewise, here bromine and here iodine. So when I will write down the basic instinct that come out here to help me, that this carbon should be more stable because it is bonded to fluorine being more electronegative. This carbon should be the second one because it is chlorine, second most electronegative. This carbon should be bonded to bromine and therefore it should be third most electronegative, and this is iodine. That is very well true. But since all are carbon, I cannot have much of difference in their electronegativities. The difference in their electronegativity values will not be too high. Now, let us go for one more parameter. Fluorine. If I want to look after the valence shell of fluorine, I'll say there is a lone pair, there is a lone pair, there is a lone pair, right? And there is no vacant orbital available with fluorine. If I go to chlorine, definitely there are 3 lone pairs with chlorine, but chlorine has vacant d orbital. Although the electronegativity of chlorine is less, but chlorine has vacant d orbital. And these vacant d orbitals are there with bromine and iodine also. They do have vacant d orbital. But the part that we discussed, the back bonding is a coordinate pi bond. Carbon atom can be really a donor atom because it is having a lone pair. Fluorine cannot be acceptor because it doesn't have vacant orbital, but bromine, iodine and chlorine, all 3 are acceptor. But look at this fact. When we did mention coordinate pi bond. A pi bond is formed by lateral overlapping of the orbital. This is a sigma bond holding them together, and this one is a pi bond. If I keep on increasing the distance between the orbitals, sigma will form, but pi interaction will be very weak. Pi interaction will not be significant. In fact, for the matter of fact, you know that oxygen form pi bond mutually. Both are 2p. But sulfur generally do not form pi bond. Nitrogen form pi bond mutually, but phosphorus doesn't form usually. So that means pi bond formation is favorable in the small size atoms. In fact, if one of the atom is from the second period, another is from the third period, it is okay. But fourth period onward, the sizes of atom are too big that pi bond formation is not at all being significant. Maybe a partial interaction there, but that is not going to play any significant role. That is not going to influence any of the property for us. So in this scenario, I can say although vacant d orbitals are there with bromine, iodine, but they cannot form that back bonding. The back bonding can only be formed by this species, right? So in this case, what will I say? CHCl3 is more acidic than CHF3 because no back bonding in any other case. Then it comes to CHBr3 and then it comes to CHI3. So this is how these strength of acids have been driven. So one factor we discuss aromatization, Second factor, we discuss this back bonding parameter. Besides these factors, there are many more factors which will come ahead. Then after these two parameters, if aromatization and back bonding is there, then we will give our answer on the basis of these parameters. Then the next parameter in the preference order coming out to be resonance. Although in some of the cases back bonding is also a type of delocalization, right? Lone pair is getting delocalized and getting converted to bond pair. But the important thing is, when there is a bond formation, there are two things. One, bond formation is always exothermic. Energy will be released from the bond. That is one part. Second, lone pair is converted to bond pair, which is more stable than lone pair. So that means there is nothing that can compensate back bonding, or likewise aromatization, because aromatic compounds are exceptionally stable because of the electron co-current that we will discuss later. So in this case, resonance will come afterward, in which we know that minus R effect that we will discuss later. What are the minus R groups? But if minus R effect is operative there, the presence of minus R effect will increase the acidic strength. Plus R effect will act the reverse way. Then coming on to minus of hyperconjugation, that is reverse hyperconjugation, which is actually not very much intended for NCERT section. So we will try to avoid this in the part of discussion. We will just refer it in terms of electronegativities. Then it comes to minus I effect. So these are the parameters in the successive decreasing order how acidic strength is going to be impacted, and what should be the priority order that we have to consider while deciding the acidic strength. The very first parameter, I am again repeating, size. Bigger atom, more stable anion. Less charge density of negative charge, more stable anion. More stable anion, stronger acid. After the size, then it comes to what? Electronegativity. More electronegativity, if sizes are comparable, definitely form stable anion. If electronegativity is also not there as a parameter and comparable electronegativity, then we come to other parameters, aromatization and back bonding. After that, we consider resonance effect. After that, we consider reverse hyperconjugation and inductive effect. And of course, when we consider resonance effect also, then we have comparison of different resonating structures. We will look after which structure is more stable, which structure is less stable, and there are plenty of parameters that we go about. But as a foundation part, I have to make this thing clear that what should be the preference order to check onto that. What is the ideal way to look at the acidic and the basic strength? Now coming on to the basic strength. Again, as I defined earlier, that a base is nothing but, in organic chemistry, it is mostly electron pair donor and the one that accept H+. For example, if I have taken some species B with a lone pair, combines with H+, forming BH+. In this BH plus entity, one thing is availability of lone pair. That simply means if lone pair is more available to us, it is strongly basic. More available lone pair will easily combine with H+. Easily combine with H+, that means it will take up H+ from acid easily, and therefore it is a stronger base. Second thing, stability of cation. Here I would say that more stable cation, more will be the value of Kb for this, more will be the value of Kb, stronger will be the base. Very simple the way we discussed for acid. Moreover, I know that if in the forward direction this species is in the equilibrium gaining this proton, in the backward direction this is losing this proton. And in this equilibrium I know that K equilibrium is nothing but K forward by K backward. So if K forward is bigger, K backward is going to be smaller. If K backward is bigger, K forward is going to be smaller. So simply I can say if acid is strong, its conjugate base is going to be weak. For a stronger acid, its conjugate base is weak. Although that statement itself is not complete, because with this statement you can answer 30-40% question, you cannot answer every question. To answer every question of basic strength, we have to go about this availability of lone pair and checking on the availability and stability of this cation. That we will explore in the next lecture, that is about the basic strength of whether it is amines or it is alcohols or it is ethers or it is amides. We will compare on them, and then we have a comparative study of acidic and basic parameters parallel side by side, so that I can help you to enhance your understanding and we will progress ahead with a relatively smooth and firm way. So guys, I hope you understood and some of the misconceptions got cleared off in the lecture, and hoping you to see you soon in the class whenever you guys are coming. Otherwise, we are continuing here itself. Take care and all the very best. God bless you. Done now?